Phosphorus. Phosphorus is a chemical element with symbol P and atomic number 15. Elemental phosphorus exists in two major forms, white phosphorus and red phosphorus, but because it is highly reactive, phosphorus is never found as a free element on Earth. It has a concentration in the Earth's crust of about 1 gram per kilogram. With few exceptions, minerals containing phosphorus are in the maximally oxidized state as inorganic phosphate rocks. Elemental phosphorus was first isolated in 1669 and emitted a faint glow when exposed to oxygen, hence the name, taken from Greek mythology, Phi Omega Sigma Phi Rho Omicron, meaning light bearer, referring to the morning star, the planet Venus. The term phosphorescence, meaning glow after illumination, derives from this property of phosphorus, although the word has since been used for a different physical process that produces a glow. The glow of phosphorus is caused by oxidation of the white phosphorus, a process now called chemiluminescence. Together with nitrogen, arsenic, antimony, and bismuth, phosphorus is classified as a pnictogen. Phosphorus is essential for life. Phosphates are a component of DNA, RNA, ADP, and phospholipids. Elemental phosphorus was first isolated from human urine, and bone ash was an important early phosphate source. Phosphate mines contain fossils because phosphate is present in the fossilized deposits of animal remains and excreta. Low phosphate levels are an important limit to growth in some aquatic systems. The vast majority of phosphorus compounds mined are consumed as fertilizers. Phosphate is needed to replace the phosphorus that plants remove from the soil, and its annual demand is rising nearly twice as fast as the growth of the human population. Other applications include organophosphorus compounds in detergents, pesticides, and nerve agents. Phosphorus has several allotropes that exhibit strikingly different properties. The two most common allotropes are white phosphorus and red phosphorus. From the perspective of applications and chemical literature, the most important form of elemental phosphorus is white phosphorus, often abbreviated as WP. It is a soft, waxy solid which consists of tetrahedral P4 molecules, in which each atom is bound to the other 3 atoms by a single bond. This P4 tetrahedron is also present in liquid and gaseous phosphorus up to the temperature of 800 degrees C when it starts decomposing to P2 molecules. White phosphorus exists in 2 crystalline forms, alpha and beta. At room temperature, the alpha form is stable, which is more common, and it has cubic crystal structure, and at 195.2 K, it transforms into beta form, which has hexagonal crystal structure. These forms differ in terms of the relative orientations of the constituent P4 tetrahedra. White phosphorus is the least stable, the most reactive, the most volatile, the least dense, and the most toxic of the allotropes. White phosphorus gradually changes to red phosphorus. This transformation is accelerated by light and heat, and samples of white phosphorus almost always contain some red phosphorus and accordingly appear yellow. For this reason, white phosphorus that is aged or otherwise impure is also called yellow phosphorus. When exposed to oxygen, white phosphorus glows in the dark with a very faint tinge of green and blue. It is highly flammable and pyrophoric upon contact with air. Owing to its pyrophoricity, white phosphorus is used as an additive in napalm. The odor of combustion of this form has a characteristic garlic smell, and samples are commonly coated with white phosphorus pentoxide, which consists of P4010 tetrahedra with oxygen inserted between the phosphorus atoms and at their vertices. White phosphorus is insoluble in water but soluble in carbon disulfide. Thermolysis of P4 at 1100 Kelvin gives diphosphorus, P2. This species is not stable as a solid or liquid. The dimeric unit contains a triple bond and is analogous to N2. It can also be generated as a transient intermediate in solution by thermolysis of organophosphorus precursor reagents. At still higher temperatures, P2 dissociates into atomic P. Red phosphorus is polymeric in structure. It can be viewed as a derivative of P4 wherein one pp bond is broken, and one additional bond is formed with the neighboring tetrahedron, resulting in a chain-like structure. Red phosphorus may be formed by heating white phosphorus to 250 degrees C or by exposing white phosphorus to sunlight. Phosphorus after this treatment is amorphous. Upon further heating, this material crystallizes. In this sense, red phosphorus is not an allotrope, but rather an intermediate phase between the white and violet phosphorus, and most of its properties have a range of values. For example, freshly prepared, bright red phosphorus is highly reactive and ignites at about 300 degrees C, though it is more stable than white phosphorus, which ignites at about 30 degrees C. After prolonged heating or storage, the color darkens. The resulting product is more stable and does not spontaneously ignite in air. Violet phosphorus is a form of phosphorus that can be produced by day-long annealing of red phosphorus above 550 degrees C. In 1865, Hittorf discovered that when phosphorus was recrystallized from molten lead, a red/purple form is obtained. Therefore, this form is sometimes known as Hittorf's phosphorus. Black phosphorus is the least reactive allotrope and the thermodynamically stable form below 550 degrees C. It is also known as beta metallic phosphorus and has a structure somewhat resembling that of graphite. It is obtained by heating white phosphorus under high pressures. It can also be produced at ambient conditions using metal salts, e.g. mercury, as catalysts. In appearance, properties, and structure, it resembles graphite, being black and flaky, a conductor of electricity, and has puckered sheets of linked atoms. Another form, scarlet phosphorus, is obtained by allowing a solution of white phosphorus in carbon disulfide to evaporate in sunlight. When first isolated, it was observed that the green glow emanating from white phosphorus would persist for a time in a stoppered jar, but then cease. Robert Boyle in the 1680s ascribed it to debilitation of the air. Actually, it is oxygen being consumed. By the 18th century, it was known that in pure oxygen, phosphorus does not glow at all. There is only a range of partial pressures at which it does. Heat can be applied to drive the reaction at higher pressures. In 1974, the glow was explained by R.J. Van Zee and A.U. Kahn. A reaction with oxygen takes place at the surface of the solid phosphorus, forming the short-lived molecules HPO and P2O2 that both emit visible light. The reaction is slow and only very little of the intermediates are required to produce the luminescence, hence the extended time the glow continues in a stoppered jar. Since its discovery, phosphors and phosphorescence were used loosely to describe substances that shine in the dark without burning. Although the term phosphorescence is derived from phosphorus, the reaction that gives phosphorus its glow is properly called chemiluminescence, not phosphorescence. 23 isotopes of phosphorus are known, including all possibilities from 2,4P up to 4,6P. Only 3,1P is stable and is therefore present at 100% abundance. The half-integer nuclear spin and high abundance of 3,1P make phosphorus 31 nmr spectroscopy a very useful analytical tool in studies of phosphorus-containing samples. 2 radioactive isotopes of phosphorus have half-lives suitable for biological scientific experiments. These are: the high-energy beta particles from 3,2P penetrate skin and corneas, and any 3,2P ingested, inhaled, or absorbed is readily incorporated into bone and nucleic acids. For these reasons, Occupational Safety and Health Administration in the United States, and similar institutions in other developed countries require personnel working with 3,2P to wear lab coats, disposable gloves, and safety glasses or goggles to protect the eyes, and avoid working directly over open containers. Monitoring personal, clothing, and surface contamination is also required. Shielding requires special consideration. The high energy of the beta particles gives rise to secondary emission of X-rays via Bremsstrahlung in dense shielding materials such as lead. Therefore, the radiation must be shielded with low-density materials such as acrylic or other plastic, water, or even wood. In 2013, astronomers detected phosphorus in Cassiopeia A, which confirmed that this element is produced in supernovae as a byproduct of supernova nucleosynthesis. The phosphorus-to-iron ratio in material from the supernova remnant could be up to 100 times higher than in the Milky Way in general. Phosphorus has a concentration in the Earth's crust of about 1 gram per kilogram. It is not found free in nature, but is widely distributed in many minerals, usually as phosphates. Inorganic phosphate rock, which is partially made of apatite, is today the chief commercial source of this element. According to the U.S. Geological Survey, about 50% of the global phosphorus reserves are in the Arab nations. Large deposits of apatite are located in China, Russia, Morocco, Florida, Idaho, Tennessee, Utah, and elsewhere. Albright and Wilson in the UK and their Niagara Falls plant, for instance, were using phosphate rock in the 1890s and 1900s from Tennessee, Florida, and the Isles du Connetable. By 1950, they were using phosphate rock mainly from Tennessee and North Africa. Organic sources, namely urine, bone ash, and guano, were historically of importance but had only limited commercial success. As urine contains phosphorus, it has fertilizing qualities which are still harnessed today in some countries, including Sweden, using methods for reuse of excreta. To this end, urine can be used as a fertilizer in its pure form or part of being mixed with water in the form of sewage or sewage sludge. The most prevalent compounds of phosphorus are derivatives of phosphate, a tetrahedral anion. Phosphate is the conjugate base of phosphoric acid, which is produced on a massive scale for use in fertilizers. Being triprotic, phosphoric acid converts stepwise to 3 conjugate bases. Phosphate exhibits a tendency to form chains and rings containing POP bonds. Many polyphosphates are known, including ADP. Polyphosphates arise by dehydration of hydrogen phosphates such as HPO42 and H2PO4. For example, the industrially important pentasodium triphosphate is produced industrially by the megaton by this condensation reaction. Phosphorus pentoxide is the acid anhydride of phosphoric acid, but several intermediates between the two are known. This waxy white solid reacts vigorously with water. With metal cations, phosphate forms a variety of salts. These solids are polymeric, featuring POM linkages. When the metal cation has a charge of 2+ or 3+, the salts are generally insoluble, hence they exist as common minerals. Many phosphate salts are derived from hydrogen phosphate. PCl5 and PF5 are common compounds. PF5 is a colorless gas and the molecules have trigonal bipyramidal geometry. PCl5 is a colorless solid which has an ionic formulation of PCl4 plus PCl6, but adopts the trigonal bipyramidal geometry when molten or in the vapor phase. PBr5 is an unstable solid formulated as PBr4 plus Br and Pi5 is not known. The pentachloride and pentafluoride are Lewis acids. With fluoride, PF5 forms PF6, an anion that is isoelectronic with SF6. The most important oxyhalide is phosphorus oxychloride, which is approximately tetrahedral. Before extensive computer calculations were feasible, it was thought that bonding in phosphorus compounds involved d orbitals. Computer modeling of molecular orbital theory indicates that this bonding involves only s and p orbitals. All 4 symmetrical trihalides are well known: gaseous PF3, the yellowish liquids PCl3 and PBr3, and the solid Pi3. These materials are moisture sensitive, hydrolyzing to give phosphorus acid. The trichloride, a common reagent, is produced by chlorination of white phosphorus. The trifluoride is produced from the trichloride by halide exchange. PF3 is toxic because it binds to hemoglobin. Phosphorus oxide, P4O6 is the anhydride of P3, the minor tautomer of phosphorus acid. The structure of P4O6 is like that of P4010 without the terminal oxide groups. These compounds generally feature PP bonds. Examples include catenate derivatives of phosphine and organophosphenes. Compounds containing P equals P double bonds have also been observed, although they are rare. Phosphides arise by reaction of metals with red phosphorus. The alkali metals and alkaline earth metals can form ionic compounds containing the phosphide ion, P3. These compounds react with water to form phosphine. Other phosphides, for example Na3P7, are known for these reactive metals. With the transition metals as well as the monophosphides, there are metal-rich phosphides, which are generally hard refractory compounds with a metallic luster, and phosphorus-rich phosphides, which are less stable and include semiconductors. Schreibersite is a naturally occurring metal-rich phosphide found in meteorites. The structures of the metal-rich and phosphorus-rich phosphides can be complex. Phosphine and its organic derivatives are structural analogues of ammonia, but the bond angles at phosphorus are closer to 90 degrees for phosphine and its organic derivatives. It is an ill-smelling, toxic compound. Phosphorus has an oxidation number of -3 in phosphine. Phosphine is produced by hydrolysis of calcium phosphide, Ca3P2. Unlike ammonia, phosphine is oxidized by air. Phosphine is also far less basic than ammonia. Other phosphines are known which contain chains of up to 9 phosphorus atoms and have the formula PNHN+2. The highly flammable gas diphosphine is an analog of hydrazine. Phosphorus oxoacids are extensive, often commercially important, and sometimes structurally complicated. They all have acidic protons bound to oxygen atoms. Some have non-acidic protons that are bonded directly to phosphorus, and some contain phosphorus bonds. Although many oxoacids of phosphorus are formed, only 9 are commercially important, and 3 of them, hypophosphorus acid, phosphorus acid, and phosphoric acid, are particularly important. The PN molecule is considered unstable, but is a product of crystalline phosphorus nitride decomposition at 1100 K. Similarly, H2PN is considered unstable, and phosphorus nitride halogens like F2PN, Cl2PN, Br2PN, and I2PN oligomers into cyclic polyphosphazines. For example, compounds of the formula N exist mainly as rings such as the trimer hexachlorophosphazine. The phosphazines arise by treatment of phosphorus pentachloride with ammonium chloride. PCl5 plus NH4Cl1/Nn plus 4HCl. When the chloride groups are replaced by alkoxide, a family of polymers is produced with potentially useful properties. Phosphorus forms a wide range of sulfides, where the phosphorus can be in P, or other oxidation states. The most famous is the threefold symmetric P4S3, which is used in strike anywhere matches. P4S10 and P4010 have analogous structures. Mixed oxyhalides and oxyhydrides of phosphorus are almost unknown. Compounds with PC and POC bonds are often classified as organophosphorus compounds. They are widely used commercially. The PCl3 serves as a source of P3+ en routes to organophosphorus compounds. For example, it is the precursor to triphenylphosphine. Treatment of phosphorus trihalides with alcohols and phenols gives phosphites, e.g. triphenylphosphite. Similar reactions occur for phosphorus oxychloride, affording triphenylphosphate. The name Phosphorus in ancient Greece was the name for the planet Venus and is derived from the Greek words, which roughly translates as light bringer or light carrier. Hesperus or Hesperinus and Eosphorus are close homologues, and also associated with Phosphorus the planet. According to the Oxford English Dictionary, the correct spelling of the element is phosphorus. The word phosphorus is the adjectival form of the P3+ valence, so, just as sulfur forms sulfurous and sulfuric compounds, phosphorus forms phosphorus compounds and P5+ valence phosphoric compounds. The discovery of phosphorus, the first element to be discovered that was not known since ancient times, is credited to the German alchemist Hennig Brand in 1669, although other chemists might have discovered phosphorus around the same time. Brand experimented with urine, which contains considerable quantities of dissolved phosphates from normal metabolism. Working in Hamburg, Brand attempted to create the fabled philosopher's stone through the distillation of some salts by evaporating urine, and in the process produced a white material that glowed in the dark and burned brilliantly. It was named Phosphorus mirabilis. Brand's process originally involved letting urine stand for days until it gave off a terrible smell. Then he boiled it down to a paste, heated this paste to a high temperature, and led the vapors through water, where he hoped they would condense to gold. Instead, he obtained a white, waxy substance that glowed in the dark. Brand had discovered phosphorus. We now know that Brand produced ammonium sodium hydrogen phosphate, NaHPO4. While the quantities were essentially correct, it was unnecessary to allow the urine to rot first. Later scientists discovered that fresh urine yielded the same amount of phosphorus. Brand at first tried to keep the method secret, but later sold the recipe for 200 thalers to D. Kraft from Dresden, who could now make it as well, and toured much of Europe with it, including England, where he met with Robert Boyle. The secret that it was made from urine leaked out, and first Johann Kunkel in Sweden and later Boyle in London also managed to make phosphorus, possibly with the aid of his assistant, Ambrose Godfrey Hankwitz, who later made a business of the manufacture of phosphorus. Boyle states that Kraft gave him no information as to the preparation of phosphorus other than that it was derived from somewhat that belonged to the body of man. This gave Boyle a valuable clue, so that he, too, managed to make phosphorus, and published the method of its manufacture. Later he improved Brand's process by using sand in the reaction. Robert Boyle was the first to use phosphorus to ignite sulfur-tipped wooden splints, forerunners of our modern matches, in 1680. Phosphorus was the 13th element to be discovered. For this reason, and due to its use in explosives, poisons and nerve agents, it is sometimes referred to as the devil's element. In 1769, Johann Gottlieb Gahn and Carl Wilhelm Scheele showed that calcium phosphate too is found in bones, and they obtained elemental phosphorus from bone ash. Antoine Lavoisier recognized phosphorus as an element in 1777. Bone ash was the major source of phosphorus until the 1840s. The method started by roasting bones, then employed the use of clay retorts encased in a very hot brick furnace to distill out the highly toxic elemental phosphorus product. Alternately, precipitated phosphates could be made from ground-up bones that had been degreased and treated with strong acids. White phosphorus could then be made by heating the precipitated phosphates, mixed with ground coal or charcoal in an iron pot, and distilling off phosphorus vapor in a retort. Carbon monoxide and other flammable gases produced during the reduction process were burnt off in a flare stack. In the 1840s, world phosphate production turned to the mining of tropical island deposits formed from bird and bat guano. These became an important source of phosphates for fertilizer in the latter half of the 19th century. Phosphate rock, which usually contains calcium phosphate, was first used in 1850 to make phosphorus, and following the introduction of the electric arc furnace by James Burgess Reedman in 1888, elemental phosphorus production switched from the bone ash heating to electric arc production from phosphate rock. After the depletion of world guano sources about the same time, mineral phosphates became the major source of phosphate fertilizer production. Phosphate rock production greatly increased after World War II, and remains the primary global source of phosphorus and phosphorus chemicals today. See the article on peak phosphorus for more information on the history and present state of phosphate mining. Phosphate rock remains a feedstock in the fertilizer industry, where it is treated with sulfuric acid to produce various superphosphate fertilizer products. White phosphorus was first made commercially in the 19th century for the match industry. This used bone ash for a phosphate source, as described above. The bone ash process became obsolete when the submerged arc furnace for phosphorus production was introduced to reduce phosphate rock. The electric furnace method allowed production to increase to the point where phosphorus could be used in weapons of war. In World War I, it was used in incendiaries, smoke screens, and tracer bullets. A special incendiary bullet was developed to shoot at hydrogen-filled zeppelins over Britain. During World War II, Molotov cocktails made of phosphorus dissolved in petrol were distributed in Britain to specially selected civilians within the British resistance operation for defence, and phosphorus incendiary bombs were used in war on a large scale. Burning phosphorus is difficult to extinguish, and if it splashes onto human skin it has horrific effects. Early matches used white phosphorus in their composition, which was dangerous due to its toxicity. Murders, suicides, and accidental poisonings resulted from its use. In addition, exposure to the vapors gave match workers a severe necrosis of the bones of the jaw, the infamous phossy jaw. When a safe process for manufacturing red phosphorus was discovered, with its far lower flammability and toxicity, laws were enacted, under the Berne Convention, requiring its adoption as a safer alternative for match manufacture. The toxicity of white phosphorus led to discontinuation of its use in matches. The Allies used phosphorus incendiary bombs in World War II to destroy Hamburg, the place where the miraculous bearer of light was first discovered. Most production of phosphorus-bearing material is for agriculture fertilizers. For this purpose, phosphate minerals are converted to phosphoric acid. It follows two distinct chemical routes, the main one being treatment of phosphate minerals with sulfuric acid. The other process utilizes white phosphorus, which may be produced by reaction and distillation from very low-grade phosphate sources. The white phosphorus is then oxidized to phosphoric acid and subsequently neutralized with base to give phosphate salts. Phosphoric acid produced from white phosphorus is relatively pure and is the main route for the production of phosphates for all purposes, including detergent production. In the early 1990s, Albright and Wilson's purified wet phosphoric acid business was being adversely affected by phosphate rock sales by China and the entry of their long-standing Moroccan phosphate suppliers into the purified wet phosphoric acid business. In 2017, the USGS estimated 68 billion tons of world reserves, where reserve figures refer to the amount assumed recoverable at current market prices. 0.261 billion tons were mined in 2016. Critical to contemporary agriculture, its annual demand is rising nearly twice as fast as the growth of the human population. The production of phosphorus may have peaked already, leading to the possibility of global shortages by 2040. In 2007, at the rate of consumption, the supply of phosphorus was estimated to run out in 345 years. However, some scientists now believe that a peak phosphorus will occur in 30 years and that at current rates, reserves will be depleted in the next 50 to 100 years. Co-founder of Boston-based investment firm and environmental foundation Jeremy Grantham wrote in Nature in November 2012 that consumption of the element must be drastically reduced in the next 20 to 40 years or we will begin to starve. According to N. Greenwood and A. Earnshaw, authors of the textbook, Chemistry of the Elements, however, phosphorus comprises about 0.1% by mass of the average rock, and consequently the Earth's supply is vast, although dilute. Presently, about 1 million short tons of elemental phosphorus is produced annually. Calcium phosphate, mostly mined in Florida and North Africa, can be heated to 1,201,500 degrees C with sand, which is mostly SiO2, and coke to produce vaporized P4. The product is subsequently condensed into a white powder under water to prevent oxidation by air. Even underwater, white phosphorus is slowly converted to the more stable red phosphorus allotrope. The chemical equation for this process when starting with fluoroapatite, a common phosphate mineral, is. Side products from this process include ferrophosphorus, a crude form of Fe2P, resulting from iron impurities in the mineral precursors. The silicate slag is a useful construction material. The fluoride is sometimes recovered for use in water fluoridation. More problematic is a mud containing significant amounts of white phosphorus. Production of white phosphorus is conducted in large facilities in part because it is energy intensive. The white phosphorus is transported in molten form. Some major accidents have occurred during transportation. Train derailments at Brownston, Nebraska, and Miamisburg, Ohio led to large fires. The worst incident in recent times was an environmental contamination in 1968 when the sea was polluted from spillage and/or inadequately treated sewage from a white phosphorus plant at Placentia Bay, Newfoundland. Another process by which elemental phosphorus is extracted includes applying at high temperatures. Historically, before the development of mineral-based extractions, white phosphorus was isolated on an industrial scale from bone ash. In this process, the trichalcium phosphate in bone ash is converted to monocalcium phosphate with sulfuric acid. Monocalcium phosphate is then dehydrated to the corresponding metaphosphate. When ignited to a white heat with charcoal, calcium metaphosphate yields 2/3 of its weight of white phosphorus, while 1/3 of the phosphorus remains in the residue as calcium orthophosphate. Phosphorus is an essential plant nutrient, and the bulk of all phosphorus production is in concentrated phosphoric acids for agriculture fertilizers, containing as much as 70% to 75% P2O5. Its annual demand is rising nearly twice as fast as the growth of the human population. That led to large increase in phosphate production in the second half of the 20th century. Artificial phosphate fertilization is necessary because phosphorus is essential to all living organisms. Natural phosphorus-bearing compounds are mostly insoluble and inaccessible to plants, and the natural cycle of phosphorus is very slow. Fertilizer is often in the form of superphosphate of lime, a mixture of calcium dihydrogen phosphate 2, and calcium sulfate dihydrate produced reacting sulfuric acid and water with calcium phosphate. Processing phosphate minerals with sulfuric acid for obtaining fertilizer is so important to the global economy that this is the primary industrial market for sulfuric acid and the greatest industrial use of elemental sulfur. White phosphorus is widely used to make organophosphorus compounds through intermediate phosphorus chlorides and 2-phosphorus sulfides, phosphorus pentasulfide and phosphorus sesquisulfide. Organophosphorus compounds have many applications, including in plastic isers, flame retardants, pesticides, extraction agents, nerve agents, and water treatment. Phosphorus is also an important component in steel production, in the making of phosphor bronze, and in many other related products. Phosphorus is added to metallic copper during its smelting process to react with oxygen present as an impurity in copper and to produce phosphorus-containing copper alloys with a higher hydrogen embrittlement resistance than normal copper. The first striking match with a phosphorus head was invented by Charles Soria in 1830. These matches were made with heads of white phosphorus, an oxygen-releasing compound, and a binder. They were poisonous to the workers in manufacture, sensitive to storage conditions, toxic if ingested, and hazardous when accidentally ignited on a rough surface. Production in several countries was banned between 1872 and 1925. The International Berne Convention, ratified in 1906, prohibited the use of white phosphorus in matches. In consequence, the strike anywhere matches were gradually replaced by safety matches, wherein the white phosphorus was replaced by phosphorus sesquisulfide, sulfur, or antimony sulfide. Such matches are difficult to ignite on any surface other than a special strip. The strip contains red phosphorus that heats up upon striking, reacts with the oxygen-releasing compound in the head, and ignites the flammable material of the head. Sodium triphosphate made from phosphoric acid is used in laundry detergents in some countries, but banned for this use in others. This compound softens the water to enhance the performance of the detergents and to prevent pipe/boiler tube corrosion. Inorganic phosphorus in the form of the phosphate PO34 is required for all known forms of life. Phosphorus plays a major role in the structural framework of DNA and RNA. Living cells use phosphate to transport cellular energy with adenosine triphosphate, necessary for every cellular process that uses energy. ADP is also important for phosphorylation, a key regulatory event in cells.